Okay, this is Derek Thompson, and this is exercise 36 in the Stewart calculus book in section 1.1. And this is about big F of x is equal to the absolute value of 2x plus 1. And the directions are to find the domain and sketch the graph of the function. Now, the first thing about the domain, the only issues we know of right now are when you have a negative square root or you divide by 0. But we don't have any division here or any square roots, so the domain here is all reals. So you can just write minus infinity to infinity for interval notation. Now, before I talk about how to graph this function, I want to just talk about absolute value x in general. So absolute value x is a piecewise function, and it's, if you think about the absolute value of, say, 7, it's just 7. It's the same number when you have a positive number or 0. The absolute value of 0 is just 0. But if you take a negative number, and say the absolute value of negative 11 is just 11, what you've done is you've multiplied the number by minus 1. So that's minus x when x is less than 0. But I want you to forget about the x, and I want you to think just about maybe when you were in elementary trying to do algebra and they just had like a blank or a question mark. Then whatever the question mark inside the absolute value is, you just do the same thing again if it's positive, and you just negate it, multiply it by negative 1 if it's negative. So let's apply that same concept to our big function f of x. So if I have big f of x here, this is the absolute value of 2x plus 1, then that is a piecewise function, and it's the same as it was when 2x plus 1 is positive, or 0, but it's the negative of the entire expression that it used to be when 2x plus 1 is negative. So I apply the same principle that I did to absolute value x. I just think about what's in the absolute value. If that thing is positive or 0, then I leave it alone. But if it's negative, then I multiply the whole thing by minus 1. Now what I'd like to do is I'd like to figure out where is 2x plus 1 0, because that's the turning point of the piecewise function. That's where the piecewise function switches, right, when it's 0. So let's check that real quick. So I'm doing this part because I want to know where the piecewise function switches, and that is when x is minus 1/2. Alright, so let's go back to our piecewise function again, and I can just erase here, and I know the switching point because I don't like that expression. That's a little bit complicated. That expression is the same as just saying x is greater than or equal to minus 1/2, and then x is less than minus 1/2. That is when I'd switch from one expression to the other. And you know these expressions, they're both just lines. This is 2x plus 1 means the slope is 2 and the y-intercept is 1. And then the bottom one is really minus 2x minus 1, so the y-intercept would be minus 1, and the slope would be minus 2x. So let's try to graph that. Alright, so now I've got some graph paper here. A little sloppy. So if, let's say right here is minus 1, and then minus 2, minus 3. So right there is minus 1/2. And so that, from there on, I'm going to have the positive slope, and I'm going to have the y-intercept 1, and I'm going to have a slope of up 2 over 2. So, excuse me, up 2 over 1. So it should go through, when x is 1, it should be 3. So there's that point 1, 3. But beforehand, it's going to have the y-intercept minus 1 and a negative 2 slope. So it's going to look like this. Let me try to draw it a little better. Except, obviously, I don't need this intercept because it's defined by the positive slope. So, you can see it still kind of makes the V shape that the original absolute value x makes. It's just been shifted around. So your final answer would be this graph together with the fact that the domain is all reals, and you can see it's defined at every x.